So we did derivatives with polar coordinates. So we're going to start into integrals with polar coordinates today. So we're going to come up with a way of finding area of regions expressed in polar coordinates, and we're going to use basically we're going to subdivide them into small pieces of circles. So let's remember, math people always love when we can say recall. But we're going to talk about the area of a sector of a circle. So we have a sector of a circle. Our angle here is theta, and this is r. So the area of that sector is 1/2 r squared theta. And the way I think about it, we remember it is this is kind of like a triangle. The side of the triangle is r. The arc length is r theta. So the area is 1/2 the base r theta times the height, which is r. So that's a way you can remember that formula. So what we're going to do is subdivide our polar region expressed in polar coordinates into tiny little circular sectors. So we're going to say we have some function r equals some f of theta. And we want the area from theta equals some angle alpha to some other angle beta. So what we're going to do is, we did this a lot already, we're going to subdivide our region into n subintervals, and then we're going to sum the area of those little sectors over that region, and then take the limit as the number of our subintervals, as our subintervals get smaller and smaller. So just a quick sketch of what we're talking about. Here's our polar region, and we're finding the area from, here's our two radii, and here we're at theta equals alpha, and up here we're at theta equals beta, and we're going to divide this into tiny little sectors. I'm going to draw those in blue here, and this little angle is going to be delta theta, and the radius at that little interval is going to be our r sub I, the radius at the in the ith subinterval. So the radius r sub I, the radius at the ith subinterval, equals f of theta sub I, whatever our theta is at that particular interval, and each interval is going to have this central angle, this delta theta. So our total area is approximately, we're going to sum up all those little sectors. So we're adding them, however many sectors we have, 1/2 f of theta sub I squared delta theta. And we're just going to sum that over our region. And then eventually we're going to subdivide our region into smaller and smaller sectors. Delta theta gets smaller and smaller, and then this sum becomes an integral. One of our favorite things. So our area in the limit, I'm going to write our area is 1/2 the integral from alpha to beta f of theta squared d theta. And our conditions, we're saying that f, our radius, is non-negative, so it's 0 or positive on this interval. And we are saying that 0 is less than or equal to beta minus alpha, less than or equal to 2 pi. So we want our radius to be positive, and we don't want to go around. We have to be aware that we may of our limits of integration, how many times we're tracing the curve on that limit. So we want to make sure we're tracing. Basically, the second condition is we're tracing around once. We're just being aware of how many times we're tracing around. So questions on our procedure, on our development here. All right, so let's use this to find the area of a polar region. So we're going to find the area enclosed by our favorite cardioid, r equals 2 plus 2 cosine theta. So let me grab a picture here. We've talked about this cardioid before. So there's our cardioid. So one thing that we want to be careful with when we're finding areas of polar regions is we need to make sure of our limits of integration. So so what I would do with this one is I would say when theta equals 0, my radius is 4. So I'm starting here. And then when, usually you can go by increments of pi over 2. And then when theta equals pi over 2, cosine theta is 0, and I'm up here at r equals 2. And when theta equals pi, I get down to 0. So this is, the upper half is traced between 0 and pi. So the lower half is going to be traced between 0 and 2 pi. So this is traced once. Depending on your graph, it might get traced twice on that interval, and then we'd have to take that into account with our limits of integration. And to make our lives easier, I'm going to say this graph is symmetrical, so we'll just find the area of the top half and multiply that by 2. So our area for our integral is going to be 1/2 and times 2. Make sure I put my 2 in there. 2 times 1/2, the integral from 0 to pi of, and we square r, so we get, I'm going to factor out the 2 here. So I'm going to write that as 4 times 1 plus cosine theta squared d theta. I factored out the 2 before I squared it, and then I can just square this quantity. So I can rewrite that as 4 integral from 0 to pi. Now I'm going to square this, and I get 1 plus 2 cosine theta plus cosine squared theta d theta. So we have three integrals that we have to evaluate here. The first two, integral of 1 d theta is pretty easy. The integral of 2 cosine theta d theta is pretty easy. Cosine squared d theta. What are we going to do with that? Some kind of identity. So here's a big hint. If you need this identity on a quiz or a test, I would give it to you. But this identity comes up a whole lot when we're dealing with polar coordinates. So let me write it down over here. Cosine squared theta equals 1 plus cosine 2 theta over 2. That identity for cosine squared theta, and there's a similar one for sine squared theta, comes up a whole lot in polar coordinates. So it's a good one to keep kind of close in your memory. So now we're going to rewrite our integral. So our area equals 4. I'm going to write everything out here, just making everything explicit. 1 plus 2 cosine theta plus 1 plus cosine 2 theta over 2 d theta. So that's it. That's our integral that we're going to evaluate to find our area. So we get 4 I'm just looking at what oh, okay. So I'm going to take this 1/2 from this piece, and I'm going to add it to the 1 here. So this separates into 1/2 plus cosine theta over 2. So I'm going to rewrite that as the integral from 0 to pi of 3/2 plus 2 cosine theta plus cosine 2 theta over 2 d theta. So I just took this 1/2 with this term and added it to this 1 to get the 3/2. And now we can evaluate our integral, so we get 4 times 3/2 theta plus 2 sine theta plus sine 2 theta over 4 when we evaluate all of those, and we're evaluating on 0 to pi. And when we add all this up, when we do our evaluation, this comes out to be 6 pi. So the area of that cardioid from 0 to 2 pi is 6 pi square units. Questions on what we did there? So this again, this identity comes up a lot because we end up with cosine squareds quite a bit when we're dealing with areas of polar curves. All right, so things start to get interesting when we talk about polar curves intersecting, and we want to find the area between two curves, the common interior of two curves. So we'll talk about the simple case first, and then we'll talk about why it gets more complicated than just that simple case. Is everybody good with this example? Okay. So area. Area between curves. So the simple case. And it's nice when it works out this way, but it often is not quite this easy. So we're talking about the area between two polar curves. So let me sketch out what we're talking about here. There's our pi over 2 axis and our theta equals 0 axis. And we have two polar curves here. This is R2, and this is R1. And here we're at theta equals alpha and theta equals beta. So our area is just the area between these two curves, just like we might expect. Our area is 1/2 our integral from alpha to beta of R2 squared d theta minus 1/2 the integral from alpha to beta of R1 squared d theta. So we're just subtracting the two, the big circle minus the little circle. And we can rewrite that if we want as 1/2 the integral from alpha to beta of R2 squared minus R1 squared d theta. So just like we did in rectangular coordinates, and a lot of people remember, we're just taking the big circle minus the little circle. So that's the easy case when that happens. Often it's not quite that simple to find the area between two curves. And let me show you why that might be. So let me grab another picture here. All right, so let me shrink this down a little bit. And I'm going to grab a picture of this. All right, and so here's the intersection of these two polar curves. R equals 3 cosine theta, the circle, and R and G of theta is 4 cosine 3 theta, the rose curve here. If we want to find the area of the common interior of these two curves, so this area in here, it is a little more complicated than just taking the circle minus the rose curve. Because what's happening here is, if we think of our radius sweeping out the area. So let me draw in a radius here to here, and a radius to here. So from theta equals 0 to this point of intersection, the radius is only sweeping out the area of this little piece. And from theta equals whatever this intersection is to, I believe this is pi over 2, our radius is only sweeping out this little area. So in order to find the area of this interior region, we need to break it into 3 different pieces and use 3 different integrals. So for this particular curve, it's not as simple as the big circle minus the little circle. You have to look at the region and decide how to break up our region of integration. If we wanted this exterior region, we could take the area of the rose curve minus the area of the circle on that interval. But this interior region is a little more complicated. Let me grab a picture of another one where we have to take that into consideration. So here's a cardioid, intersection of a cardioid and a circle. So let me grab a picture of that one. So if we're looking at the intersection of those two, to get this interior region, splitting it up like so. From theta equals whatever it is here to this point of intersection, our radius is only tracing out the area of the circle. And then from here, our radius traces out, sweeps out the area of the cardioid. And then back here, our radius is sweeping out the area of the circle again. So this interior region is a little more complicated than just the big circle minus the little circle. So sometimes if we were finding the area of this exterior region, the area between these two curves, then I could just take the area of the circle minus the area of the cardioid from these points of intersection. But the interior region is a little more complicated. So I want you guys to be aware of this when you're looking at these polar regions. One thing that helps is if you actually visualize that radius sweeping out the area. So that's when I look at these regions, these polar regions, I think of, okay, the radius is sweeping across here, and what curve is it touching? Where is the area being swept out? So let me show you some pictures of that. I have an animation for that. Just some visualization of area being swept out in polar coordinates. I already have it open. There we go. So let's look at, so here's a cardioid. And so I'm just going to trace out, the radius is going to sweep out the area of this cardioid. So this is how I talk about visualizing it. So there's that area being swept out in there. So we can visualize the radius sweeping across, and it sweeps out that area. And then we go around here. If we have a more complicated curve, like this limacon, we watch the radius sweep out the area here from theta equals 0 to pi. The entire area gets swept out. And then as we go around to 2 pi, this interior, the inner loop, gets swept out again. And it's finally not until we get almost around to 2 pi that this little piece gets swept out. So if we just wanted to find the area in here, we would have to be aware that this little piece gets swept out twice as we go from 0 to 2 pi, as we visualize that radius sweeping around there. So it's not until we get to there that that inner loop gets traced out. And then if we have a spiral, for example, we're sweeping out the area here. We get that much of it swept out between 0 and 2 pi. And then as we go around again, we sweep out this little inner piece a second time. So when we've gone around to here, this region from here to here has been swept out twice. And then we go for this area, the entire area that we've swept out before gets swept out again. So each time we go around, it's sweeping out an area that we've already swept out previously. So if we're finding the area of a spiral, we have to take that into consideration as we're finding our area. So if we wanted the area in here, we'd have to realize that the smaller piece gets swept out twice as we sweep out that area. So visualizing that radius sweeping out the area can really help when you're to try to come up with your limits of integration when you're finding areas of polar regions. All right, so let's go back to our notes. The other thing that comes up, the other thing that can come up when we're finding intersections of polar regions is that solving simultaneous equations may not necessarily give us all of our points of intersection. So let's talk about that really quickly. So the important thing to remember about intersections is that polar coordinates are not unique. So there are multiple representations of points in polar coordinates, and that solving the simultaneous equation, setting the two polar equations equal to each other, might not give you all the points of intersection. So in order to find them, you're going to have to graph your functions and take a look at this. So I want to give you an example of this. If we have r equals 2 sine theta and r equals 2 cosine theta. If I sketch a quick graph of this, I know my hand sketch graphs are not going to be perfect, but r equals 2 sine theta, I get a circle here, and r equals 2 cosine theta, I get a circle on the x-axis. Well, that sketch's not too bad. So it's pretty clear from the graph that these circles have 2 points of intersection. But if I set these two equal to each other, and I want to find those points of intersection, I get 2 sine theta equals 2 cosine theta. Simultaneous equations here give me tangent theta equals 1. And tangent theta equals 1 at theta equals what? Pi over 4. So this point of intersection corresponds to theta equals pi over 4. So why don't we get the point at the origin? There's 2. So what do you mean?
There's 2 points on pi over 4.
So yeah, so we can see from our graph that this angle corresponds to pi over 4, right? I think so. It does have something to do with there being 2 things, but I was thinking you were talking about that.
R equals 0 for the second one when theta equals like pi half and it equals 0 for the first one.
Okay.
Theta equals 0.
So for r equals 2 cosine theta, this is what Chopin says, equals 0 at the point 0 pi over 2. And r equals 2 sine theta equals 0 at 0 pi. So they equal, the radius is 0 at different values for theta. So they go through the origin, but at different values of theta. So it's not a simultaneous solution. So the solution r equals 0 is at different angles. So the example that I think of is like satellites that are orbiting the Earth. They might cross, their paths might cross, but that doesn't mean those satellites are going to necessarily collide, because they can be at that point in space at different times. So these two functions equal 0 at different values for theta. So that's one thing that can happen with the intersections of polar graphs. So the bottom line is often you'll have to graph these functions to make sure you get all the points of intersection. And because at the pole, r can be 0 for any particular value of theta, we have to be careful. We have to evaluate the pole separately. So bottom line is always graph your equations to make sure you get all the points of intersection. So in order to find the area of this interior region, what would we have to do? How could we split it up to find this area? Anybody have an idea? I think my first thought is to go to take the area of 2 cosine theta from pi over 4 to pi over 2. So that would give me, if I split it up like this, I would get that area. And then I could add to it the area of 2 sine theta on this interval. So we could break it into two intervals. So that's how we would have to tackle that. All right, questions? Okay. Homework? And there you go.